Exponential growth and decay. So I'm going to kind of lead you through one problem here and then leave you with a problem to kind of try on your own before you start into the second video. And you're also going to practice some problems, in between as well. Some practice problems will be given to you for you to work on, and we'll talk about in lecture. But here, the population in Sorrentinaville is doubling every 15 years. How long will it take for the population to become 20 times its present amount? One of the things that sometimes throws students off on these problems, they always think you have to be given an initial amount, and you don't. We don't know how many people are in Sorrentinaville right now. Could be 20 people, could be 1,000 people, could be 5 people. I don't know. Um, I'm hoping it's probably an even number if it's doubling every 15 years. So I'm hoping that it's like, I have something that would indicate that there was doubling going on, but not necessary. Um, so for me to answer this question, I have to kind of go with the fact that, well, I'm saying here that the population is going to be the result of me taking an initial population and multiplying it by some sort of exponential statement, where A is a base, T is an amount of time. And what's going on here, since we're doubling every 15 years, what's going to happen is, first I want to find A with this. That's my general procedure. Okay, this is a standard format that I have for most of these problems. P is the final population or final amount. P of 0 is the initial amount. A is what we call just basically an exponential base that we have to determine. T is your amount of time. A lot of times it could be in years, but it could be any other amount of time as well. So I want to find A first. So we're told P of 0 is a constant because it's still our starting population. I just don't know what it is. Okay. The P I have on the left, the final population, is a variable because it depends on how long I let this growth go on. And that's where T comes in. It's the other variable. So what's happening with this is at the end of 15 years, I end up with twice my original amount. That's why you see me having 2 times P sub 0 on the other side now. The reason why it doesn't matter what my initial population is because when I go through the process here, my next step to try to solve for A is I would divide both sides by the original amount and they would cancel. So I know that A to the 15th power equals 2, which means that A is going to be the 15th root of 2, which is about 1.04729. Now, I tend to save that value, or I just basically use the 15th root of 2 when I go and do the rest of the work in this, so I'm not rounding anything or over rounding something. But sometimes it's a good idea to know what A is numerically like this, because when I have a setup like this and I'm looking for this A, if A is more than 1, it's a growth. And if A is less than 1, but still positive, it's a decay. And here, since I'm saying I have a growth, and this is mentioned, and I'm seeing a value of A that indicates growth, that's a good sign. So, the formula I now have is essentially that my final population amount is going to be P sub 0 times 1.04729 to the T power. Now again, I'm writing those 5 decimal places. The calculator certainly had more shown, and the calculator has even farther more saved, or saved in its memory that it's not showing me. That's why, once I calculate what A is on my calculator, I'll store it in the memory and use that through my rest of my calculations. So, I might be writing 1.04729 here, but I'm using the entire decimal that my calculator has in its memory, again, to avoid rounding just a little bit too much. So now I'm ready to answer the question. How long will it take for the population to become 20 times its present amount? The present amount being P sub 0. So I want the final amount to be 20 times the original amount. I'm looking for the time. Again, I'm going to divide both sides by P sub 0, and they would cancel on both sides. So I'm looking at I'm looking to solve the equation 20 equals 1.04729 to the t power, which means I'm going to be doing a log base 1.04729 of 20, which is the same thing as the log of 20 over the log of 1.04729. Now, anywhere you see this 1.04729 again, I am technically using the value that's on my calculator, not this rounded value you see here. And if I do that correctly, I get about 64.83 years. So what it's telling me is with a doubling every 15 years, I should expect to have 20 times the original the amount I have now after 64.83 years.